Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this chapter, we're going to look at the naive Bayes data mining technique. So what does naive Bayes do? Well, it is not a single algorithm, but a family of classification algorithms that share one common assumption. Every feature of the data being classified is independent of all the other features in the class, and that's an important concept. That's why it's called naive Bayes. For example, a fruit would be considered to be an apple if it's red, round, and about 4 inches in diameter. A naive Bayes classifier considers each of those features to contribute independently to the probability that this fruit is an apple, regardless of any other possible correlations that might exist between color and roundness and diameter. Two features would be considered independent when the value of one feature has no effect on the other. Let's take an example of a data set that contains a patient's information, like pulse, cholesterol, weight, height, zip code. Now, in a naive Bayes model, all of those would be treated independently of each other. And for this data set, it's reasonable to assume that a patient's height and zip code are independent of each other, since the height and zip code have little to do with one another. But, we don't stop there. There are other features and are they independent? The answer, sadly, is no. There are 3 feature relationships which are not independent. If height increases, weight likely is going to increase. And if cholesterol increases, so will weight. And if cholesterol increases, pulse is likely to increase. So, in most experience, the features of a data set are generally not all independent. So, the assumption that all features of a data set are independent is precisely why it's called naive, because it's generally not the case from experience that all features are independent. Now, in a nutshell, the theorem tells us to predict the class given a set of features using probability. And if you need to brush up on that, go back to our chapters on probability in the statistics portion of the class. But the simplified equation looks below, and we're going to go into it in detail on the next slide. But for now, this equation means the probability of class A given that features 1 and 2. In other words, if you see features 1 and 2, what's the probability that this belongs in class A? The way you read this equation for the probability of class A given features 1 and 2 is a fraction. The numerator is the probability of feature 1 multiplied by the probability of feature 2 given class A, and then multiplied by the probability of class A. And the fraction's denominator is the probability of feature 1 multiplied by the probability of feature 2. Now, this is best really done by example. Let's assume we have a training data set of 1,000 fruits, and a fruit can be a banana, an orange, or other. And then the fruit can belong to the features of long, sweet, and yellow. And so now you look at the table below, and a banana, and they get a score for long, sweet, and yellow, and an orange, and other. And what do you see in this training data set? Out of 500 bananas, 400 are long, 350 are sweet, and 450 are yellow. And out of the 300 oranges, none are long, 150 are sweet, and 300 are yellow. And out of the remaining 200 fruit, 100 are long, 150 are sweet, and 50 are yellow. So, if we are given the length, sweetness, and color of a fruit without knowing its class, we can now calculate the probability of it being a banana, orange, or other fruit. Suppose we are told that the unknown fruit is long, sweet, and yellow. Here's how we would calculate the probabilities in 4 steps. Step 1 would be to calculate the probability of the fruit as banana. And let's first recognize that this looks familiar. It's the probability of the banana given the features of yellow, long, and sweet. So probability of banana given features long, sweet, and yellow. Okay? So starting with the numerator, let's plug in everything. The probability of it being long and banana is 0.8. The probability of being sweet and banana is 0.7, and the probability of being yellow and banana is 0.9. So the probability of a banana is 500 over 1,000, or 0.5. Multiply everything together, we get 0.8, 0.7, 0.9, 0.5 equals 0.252. Now in this case we can ignore the denominator since it's going to be the same with all three calculations. So now we do the similar steps to compute the probability of it being an orange and the probability of it being other. And we get 0 for the probability of it being an orange, and we get 0.0185 for the probability of it being other. Now, since 0.252 is greater than 0.0185, the naive Bayes model would classify this long, sweet, and yellow fruit as being a banana. Just a reminder on terminology, this is supervised learning, since naive Bayes is being provided a labeled training data set in order to construct the tables that represent the probabilities. So why would we want to try to use this model if it's naive? Well, as you can see in the example, it's very easy. It's, well, simple arithmetic. It's just tallying up counts and multiplying and dividing. Once the frequency tables are calculated, classifying an unknown fruit just involves calculating a few probabilities on all of the classes and then choosing the highest probability. So despite its simplicity, naive Bayes has actually been shown to be surprisingly accurate. Number of Kaggle competitions have been won using that method. For example, it's been found especially effective at spam filtering. All right, let's take a look at a KNIME example of the naive Bayes implementation. And as you notice, the model is almost identical to what you saw in the decision trees. In fact, that's always kind of the process. So you can see I've taken, let's just remind ourselves what the data looks like. We've got a bunch of information, 78,000 rows, and we're trying to understand basically, did we win or lose this? We want to be able to predict whether we're going to win or lose a sales opportunity. And so we've recorded all this information from historical data, and that's the value we're trying to guess. And in my partitioning node, I look at the configuration. I'm putting 70% of the data into the top port for training the model, and I'm reserving 30% to test the model. So to train my model with naive Bayes, okay, I've got a few things. First, the classification column. You can see that its opportunity result is what I'm trying to look for. I want to be able to predict whether it's a win or a loss. The default probability. The probability of 0 for a given attribute, without special adjustment, it's kind of exercises as an absolute veto over a likelihood in which a probability appears as a factor. Therefore, naive Bayes model incorporates a default probability parameter that specifies a default, usually very, very small, to use in lieu of a probability of 0, which, like I said, acts as that kind of veto power. The minimum standard deviation and the threshold standard deviation function in a similar way. If you don't provide a sufficient amount of data such that you have a reasonable standard deviation, that information, this is the minimum value you have to have before that column could be considered predictable. And the threshold standard deviation, so the threshold would be the value has to be positive, and if it's not met, then the minimum standard deviation is going to be used. So that's how those two columns tie together. Finally, we got the maximum number of unique nominal values. So if you have, like you saw, the opportunity result was win-loss, there's only 2 values. You tell it at this point what's the maximum number of nominal values you want to keep, and then all the others would be considered obscure values and wouldn't be tracked with individual probabilities. You can instruct it, of course, with the checkbox. If you want to ignore missing values, you'd set that checkbox present. And the create 4.2 compatible model is just something for those who intend to take this model and export it out into another tool, which isn't going to apply here. So I'm going to go ahead and execute, and if I want, I can look at the statistics table that comes out of this, and all I see is for each count. So for each attribute, I get a count. How many wins, how many losses, how many missing values, the mean, and the standard deviation. So I can see, so for competitor type, unknown, known, and none. And I can see the breakdown, see these are the nominal values, and that it will keep, like we said in my example, up to 20 of them. All of this is the only thing necessary to compute against the real execution data. So let's go ahead and configure this, and I don't have anything to change here. I'm fine with the opportunity result prediction will come through, and if I want, again, I can append the distribution class to it, and I'll execute this. And now, when it comes to scoring, I'm going to point you back to chapter 59 on scoring on decision trees, because I walk through scoring in a very detailed way. So I'm not going to repeat that with each data mining technique. So I'll say go to if you want to understand scoring in more detail, go to chapter 59 on decision trees, and I explain in great detail what this confusion matrix is, how to interpret it, and how to understand if you're getting good results. And also the accuracy statistics. I walk through all of those so we understand the true positives, false positives, recall, precision, sensitivity, accuracy of the model, and so on. So what you can see here, by the way, is the accuracy is almost up at 80%. And my sensitivity for wins is actually at 66%. That's pretty darn good. And since that's the group I'm trying to target. So overall, that's not a bad sensitivity level. So again, if you want to understand more about how to interpret and understand all of these values, please go back and look at chapter 59 on decision trees. It's also posted here within the class materials available on YouTube. And you can see how the scoring is actually accomplished and how to interpret it. So when we compare now, let's take a look at the naive Bayes results compared to our gradient boosted tree, random forest, and all the decision trees. You can see if I look at the overall accuracy of the naive Bayes, it's actually the worst of the models so far. It's only at basically 80%, accounting for rounding there. But when I look at, again, the sensitivity to the ability to predict a win, that's at 66, almost 67%. That's just a couple of percent below the random forest, and it's actually better than the other two regular decision trees. So as I mentioned earlier in the class, this is not, even though it seems very simple and why we call it naive Bayes, doesn't mean that it's not a good model. It can actually prove to be quite effective. So the quick summary for this chapter. The naive Bayes is a data mining technique where the algorithm assumes every feature in the data being classified is independent of all the other features, hence its name, because we know often they are dependent on each other. Two features are independent when the value of one feature has no effect on the value of the other. Probability is the equation finds the probability of class A given features 1 and 2. That's the entire algorithm in its summary. That completes this chapter of the class. Feel free to move on to the next chapter.